Hey everyone, welcome back. Today we are kicking off a deep dive walkthrough of one of the most legendary textbooks in the field, The Elements of Statistical Learning by Hastie, Shirani, and Friedman. If you have ever felt intimidated by the math in this book, do not worry, we are breaking it down piece by piece. I am Shashank Sharma, your resident machine learning math nerd, and today we are starting with lesson 1, linear regression intuition. We aren't just going to look at formulas, we are going to understand the why and the how behind the simplest yet most powerful tool in your data science toolkit. So let's get started. Before we jump into the graphs, let's lay out our roadmap for this session. By the end of this video, you'll be able to answer three core questions. What does the linear regression line or hyperplane actually indicate? How does the model function look in one-dimensional and two-dimensional input features? We'll visualize the geometry. And finally, why are linear models still so popular in an era of deep learning? So we are ready. Let's get into the intuition. Take a look at this scatter plot. We have our input x on the horizontal axis and our output on the y-axis, which is vertical. The linear regression line is indicated in red, which is our best mathematical guess. Mathematically, we assume there's a linear relationship between the predictors x and the response y. But here is the technical catch. This line is also known as the expectation of y given x, written as E bracket y given x. Now, don't let the word expectation scare you. Expectation simply means average. When we look at the specific value of x, say at xi, yi, we see a cluster of potential y data points. Expectation of y given x is the average of those values. We are essentially saying if the relationship were perfectly linear, this red line is where we expect the average data point to land. In this graphical example, we only have a single predictor. But remember, as you add more predictors, like adding height, weight, salary, square footage, could be anything, this line levels up and becomes a hyperplane. What exactly is a hyperplane? More on this in just a few seconds. Visualizing data in two dimensions is easy because the hyperplane is actually a straight line. But let's try to expand our intuition. The regression line becomes a hyperplane as we add more predictors. On the left of your screen, you see the classic one-dimensional input. We have the data points x and y and a line cutting through them. But look at the three-dimensional plot on the right. Here we have two inputs, x1 and x2. Instead of a line, we now see a flat sheet. This flat sheet or surface is our hyperplane. Whether it's a line or a plane, the goal is same. The data points project to the regression line. As you can see, the projections are dropping to the line, and here in this case, the projections are dropping to the hyperplane. They drop in such a way that the sum of errors squared from the points to the hyperplane are minimized. This is why we call it a least squares fit. We are literally trying to minimize the gap. The vertical lines which you see connecting the dots to the plane, we want the total squared distance of these gaps to be as small as possible. And we will use calculus to find that out. Now, in the last slide of this lesson, let's discuss the enduring power of linear models. Why do we care? Why not just use a complex neural network for everything? There are four massive reasons why linear models are still relevant. Many of the real world systems in physics and economics scale linearly. And you will see a lot of real world data having a linear relationship with the output which we're trying to model. It's just natural for a lot of things. Mathematical flexibility. Linear models aren't stuck on linear inputs. You can transform, perform mathematical functions on the inputs. You can change the numerical values basis your custom experiments, and you retain a lot of mathematical flexibility. Occam's razor. It's the principle of Occam's razor basically states that when you have multiple explanations, often the simplest explanation is the most robust and best. Even if the data is slightly curvy, quadratic, cubic, a linear trend captures the primary signal and cuts through the noise. This is very, very helpful when we're trying to get a high level intuition or sometimes even more incisive insight. Glass box versus black box. This is a killer feature. Linear models offer high interpretability. You can look at the coefficients and know exactly how much each variable is weighted onto the output. As the slide says, while complex machine learning predicts what will happen, linear models predict and also give us good explainability. I hope you liked the lesson.